Welcome everybody. This is an SUT ECOSIGG webinar focusing on geohazards and geoengineering constraints related to tunnel valleys and their infill by Dr. Benjamin Bellwald, a Senior Geoscientist at NGI. Before we start, can you see my next slide? No, apparently not. Before we start, who are ECOSIGG? So ECOSIGG are the early careers group focusing on offshore site investigation, geotechnics, and geoscience. And we are the early careers group of OSIG, which is part of Society for Underwater Technology. So we're quite a large committee spread over various different universities and institutions and different countries as well. But on to today's webinar, it's hosted by Benjamin Bellwald, who is a Senior Geoscientist in Offshore Energy at NGI. He has a strong background in both offshore energy projects and research and development activities. He's an expert in Quaternary Geology, ultra-high resolution 3D seismic data interpretation and geo-data integration, working towards robust and data-driven ground models. And I can say from first-hand experience that Benjamin is not only an expert geologist, but an excellent educator to those new to geology. And you know, I'm only slightly forced to say that as I sit opposite him at work. So it's for the benefit of our working relationship. He holds a PhD in Marine Geology and Geophysics from the University of Bergen, and he has been working on geohazards in most sectors of the formerly glaciated European margin, and is co-chair of the wind energy community in the EAGE group. Okay, so without any further ado, Benjamin, I'll hand over to you.
Thanks a lot, Jack, for this kind and very honest words on you passed the test, so our working relation will be very fruitful for the remaining. Just a question, can you see the full screen now?
I can, yes.
Okay, good. And you can also see my cursor, or do I have to use the laser, the pointer to...
I can see your cursor, but maybe the pointer would be more obvious.
It's just because of the videos, it may be later that I have to change it, but I use the pointer. Good. So yeah, you already introduced the topic very briefly, and yeah, welcome to this. It's a big passion of mine, our glacial channels, in particular subglacial tunnel valleys. And today I would like to show you or share with you my ideas on geohazards and geoengineering constraints related to tunnel valleys and their infill. On this first slide here, actually, what I should say is also that it's not only my work, obviously. We have a big team working together on these challenges. I mentioned the ones that work closest to me in the last 2 years on this topic. I've done a lot of work in the last 2 years. I'm sure there is many more, but these are really the key, my key supporters when it comes to geohazards and geoengineering constraints in tunnel valleys and their infill. And I thought I was just visiting 2 weeks ago the castle in Oslo for the first time with my mother and partner, actually. My mother is listening, it's the first time she's listening to a webinar of mine. So welcome, Mom, and I hope you enjoy what I'm saying here. So what we see here, that's a picture or a painting that we saw in the castle during the visit. And it shows some, let's say, scientists. I guess most of them are glaciologists or geoscientists that are inspecting Tverrbren. It's in Jostedalsbren. And it's a really nice, it shows us a kind of a glacial channel. It's probably in autumn somewhere. There is no snow in the painting. It's very, also another reason why I think it's most likely autumn is you don't have a lot of meltwater coming out of this. It's quite empty. You have big boulders here, and most likely these guys are standing on a glacial till, so on over-consolidated material, I would think so. You see also nice coarse-grained moraine, most likely very blocky. And this is a bit the same. What I like about this picture is you see people with different backgrounds, most likely, if we would judge their clothing. We may have, and in offshore wind and offshore energy in general, we have different researchers with different background, engineers with different background working together. So we often have geologists. I myself, I'm a geoscientist with a strong background in quaternary geology. So I would mainly wonder here about the sediment properties, about the porosity and lithology. That's a bit the language I would use when I stand there in front of the channel here and look at the glacier. Whereas geophysicists, they're very important in this project as well, but their language is sometimes a bit different. Talk a lot about data processing, attenuation, acoustic impedance, inversion. And then, of course, we have a big share, a good amount of geotechnicians as well that are working together with these other two guys. And they talk about soil, void ratio, dissipation of energy, of course, about much more. But you see, often we're using the different language and mean the same thing. So integration and talking to each other is very key to a successful characterization of this ground, like the till or the boulders when we talk about constraints in engineering or geohazards. And then the last one could be the client. And of course, the client is interested in costs, safety, a good timeline. They may be a client could also be highly involved in the activities of the geoscientists and the geotechnicians. But we have a big team with different background that works together on these challenges that we face. Also, when we talk about tunnel valleys. So the outline of the talk that I'm going to give, first to define or to show you what is actually a tunnel valley, how do they form, where do they occur, and then going into the focus of the talk, what are actually now the geohazards and the geoengineering constraints related to the infill of the tunnel valleys and the presence of tunnel valleys, and end up the talk with how should we go forward, what are the thoughts on activities for the future to improve this. Okay, so to start just with tunnel valleys in general, and there has been a lot of research for some decades now on how tunnel valleys actually form. And there is a very nice paper from James Kirkham from 2022, where he summarizes the three formation theories. A and B, they're the best documented ones, I would say so. So in general, what we can have to say, tunnel valleys, they're subglacial canyons, and they are formed or shaped by high pressure meltwater discharge under a thick ice sheet. So you need an ice sheet, you need meltwater, and if that plays together in a proper way, you can form a tunnel valley. There are different models. So we have here the first model that is going more for a catastrophic outburst. So you may have a lake below the ice sheet, or you may have a lake dam by the ice sheet, which can drain out in a very short time frame and can erode into the sediments and form a tunnel valley. And then where you hit the ice margin, so where the ice sheet stops, you may get some boulders, you get a debris lobe with very coarse-grained sediments. But what you see, okay, there it's basically one big channel filled in with water during the discharge event, whereas in the second formation model, the surface drainage, so you have a supraglacial meltwater on the top of an ice sheet that drains to the base of an ice sheet, and you may have some, it's less energetic, it's more seasonal, and you may get several smaller channels eroding into the bigger kind of canyon. So this one is more, the model A is more high energetic, one abrupt event, whereas model B, surface drainage, is more, you have regularly spaced tunnel network with smaller channels at the base of the big canyon. So that's the two common models. I will not go into detail for the third one. They're commonly occurring along glaciated margins of the northern hemisphere, and I'm going to show that into a second. I show it to you in a second. I think what is very important for this talk, and also when we're doing offshore wind and also oil and gas CCS project, okay, the presence of the tunnel valley is one thing, but the infill is even more critical. So again, here, this is how the tunnel valley forms, a cross-section across ice sheet. You have here ice, the white thing here, that's ice, you have sediment, and then you have the active conduit, the meltwater at the base. When the ice retreats, you may have first some river here, you may have then sea level increases, you may have a lake first and then a marine environment. So you get a lot of different deposits that infill this depression or the canyon that you form by the meltwater discharge. And they can be tens to hundreds of meters deep, these valleys, and are infilled by subglacial, deglacial, or marine sediments. It can be really a multitude of type of sediments. And also important, they can contain boulders, gravels, very common, can be gas charged. And this is really important for the industry when they're doing their geohazard assessments and when they talk about foundation types for different regional settings. Good. So the first thing I said is that we need an ice sheet. I think I just have to leave the cursor here. So tunnel valleys form below ice. And when we have a look, a lot of the tunnel valleys, they occur in the North Sea. I am quite sure that you know these ones. This is a model. So it's a numerical model that shows us how the Eurasian ice sheet actually developed through the last 33,000 years. So it's the last part of the Quaternary. Quaternary is the period where you have all these nice glaciers in the Northern Hemisphere. And you see now, the glaciers are building up mainly on Fennoscandia, northern UK. In brown, maybe also important, this is now terrestrial at that time. Blue is the water, marine environment. And at around, let's say at around 20,000 we're at the moment now, you have big parts of the North Sea covered by ice. Again, this is just a numerical model, so it's not correct. We know that the ice has advanced further, but it shows you a bit how dynamic these ice sheets were throughout time. There is different type of models that simulate this. And below this ice masses now, tunnel valleys can actually form. So today, in the left here, you see we have the North Sea, where a lot of the offshore wind activities from Europe are taking place. Of course, we have the Celtic Sea, we have also the Baltic Sea that is quite big. In yellow, the outlines, that's the offshore wind farm projects by end of 2023, actually. And that's they're not all in development yet. Some are just suggested as blocks. And we really have to remember that the North Sea looked quite different throughout the time. So it was not always like a marine environment. We had rivers there. We may have had some bigger lakes there. So it's a really dynamic environment, and that's quite important for the engineering and the type of deposits that we can get. But okay, tunnel valleys. What about the geomorphology? How do they now really look like? So in planar view, they usually, wait, I went one too far. They can be either individual straight or sinuous channels, or they can be complex anastomizing or dendritic networks. So from onshore, if you know about the new, from North America, the New York Finger Lakes, it's rather individual straight channels that you see here, these lakes, that's former tunnel valleys covered by the Laurentide ice sheet. However, we see here, for instance, in the paper from Margaret Stewart, it's more, here you have a bit more complex dendritic network or anastomosing. And that's a 3D view into one of the tunnel valleys of the North Sea. Whereas here to the right, that's from Sørlige Nordsjøen 2, that's the big offshore wind farm project in Norway, where Bjørn Bowling and his team mapped out the tunnel valleys in the subsurface. You see that we have stacked tunnel valleys in the subsurface, in the very shallow subsurface. And in different units now, these are surfaces, different of this, they represent different colors here of the reflections. So you have a tunnel valley like this one here. Maybe I can activate the pointer again, laser pointer. So we have here a tunnel valley. Then we go maybe some tens meters up. Then you have a big tunnel valley going east-west. Then we jump up to the next one, and then you have more north-south, one of them. And then on the uppermost tunnel valley, or higher up tunnel valley, you have a reoccupation of this tunnel valley, but some additional tunnel valleys coming up. So really complex features, different geomorphologies, but more or less having a common origin by being subglacial meltwater channels. So I touched on this already a bit, but most of you I heard are working on or at least are based in Europe and may work in the North Sea and also the Baltic Sea, Celtic Sea. And you see now here in red, this is tunnel valleys that have been published by different authors, mapped out really a lot of tunnel valleys. Here, the lines, the thick lines here, that's the extent of the ice throughout the quaternary. We had different stages, so blue, red, or purple and green, that's different stages of the quaternary, different glaciations. And you see there a lot of tunnel valleys have been mapped out already. And I'm sure, like, if we update this map in 10 years, especially due to the offshore wind activities, we're going to have much more red in this map than we have at the moment. And then you see, oh, a lot of offshore wind farm projects, they actually collide with areas where we have a lot of tunnel valleys already. So the yellow shapes, again, are offshore wind farms. And I'm sure some of them where you may not have any mapped out tunnel valleys or published mapped out tunnel valleys, you may identify tunnel valleys that have not been published yet. So maybe a constraint there as well. And what is also quite nice, especially in northern Germany, Denmark, and Poland, we have tunnel valleys onshore that we can tie into the offshore domain potentially. And it's really nice to use these analogs, and I'm going to show you some slides. First, this one here. It's also a very recent publication where we have a very old tunnel valley. So it's several hundreds of million year old from a very old glaciation. This is from Algeria. This is the interpretation. So basically here, this thick line here, up here, that's where you have that's the flank of the tunnel valley. The reason why I show it to you, you have here really fossilized, you have bedrock, actually, sandstone, sandy diamectite, muddy diamectite. So really different type of infill also in this tunnel valley. And then here eroding into siltstone and sandstone. So really a huge feature. And we can actually go, even if we don't have data from offshore, we can go onshore and study these beautiful features onshore. And that's a big advantage, of course. So going more now into the focus topic of the talk, as the title said, geohazards and geoengineering constraints. And for that, first of all, we have to be aware of how are we dealing with these assessments of geoengineering and geohazards. So often we're combining geophysical, geotechnical, and geological data, combined with some numerical model, ground modeling, obviously, in the end as well. But this is a classical ultra-high-res 2D seismic line. This is from a project in the Baltic. And there actually, you see, okay, there is already a good share to map out based on geophysics, but we cannot map out all the units without integrating properly with the boreholes, with the CPT, and then also having geological information, CT scans from the lab. Anja is doing that quite often, X-ray scans, inspecting the pictures that are taking offshore or maybe later onshore, making some stratigraphic columns, and then coming up with a really solid subsurface model. And it's really key to integrate the geophysical, geotechnical, and geological data, because sometimes the multiple like that we saw here before, it's obviously not a proper reflection, or sometimes a borehole may not reach into the deepest part of the tunnel valley, in this case here now. So it's really important that we use all existing data that can really, in best case, complement each other. And we can reduce uncertainty also when it comes to where to set boundaries in the geology as well. So that's really beneficial to do. Good, here a video. This is now an ultra high, and I play it later as well once more because it goes quite quick. But this is an ultra high res 3D survey offshore Netherlands. It's a bin size lateral resolution of 1 meter, so fantastic resolution. And basically here I scan through a tunnel valley. So this tunnel valley, let me play the video again because it went quite quick. So here you see in the blue, that's the deeper part, that's the tunnel valley. Here is the neighborhood, the plains next to it. And you see we can identify a multitude of landforms, deposits, when we're doing this type of images. This is a spectral decomposition. So you take just some parts of the frequency content, and that allows you now to, you see much more in the picture below compared to above. This is just mapping out the depth. Whereas here now you see some circular depressions, you see some lobes coming into here. I show you some zooms of this survey later, but it's really beneficial to use the best resolution, and the geophysical survey companies, they're pushing into the direction now to get really meter or even sub-meter scale lateral resolution and decimeter scale vertical resolution. Here, that's a short publicity spoiler. A big group is working now together to make a review on marine geohazards and geoengineering constraints on the formerly glaciated European margin. So it's work in progress, but we're gonna soon submit the paper to Earth and Science Review. So it's quite it's a big work, and really big thanks to all of these contributors to that piece of work. And you're gonna please let me know, give me after the talk, really share your thoughts with me about marine geohazards and geoengineering constraints on glaciated margins. I'm really interested in what you think are key geohazards, not only in tunnel valleys. I talk here now about tunnel valleys mainly, but I'm interested, as a quaternary geologist, I'm interested in any type of geohazards on glaciated margins, be it on European margin or also Laurentide or North America, wherever. It's really interested, Antarctica, Greenland, obviously as well. So, but now the talk is about tunnel valleys, not about all of the glacial deposits. And we have actually a paper for the GET conference in EAGE. It's to be held in November this year, about exactly this topic. And this is kind of a conclusion on what we think are the main geohazards and geoengineering constraints. I'm gonna go one by one through that. And here is a conceptual sketch on how they look like, how they could look like in stratigraphy. And in order that you a bit can understand how big of a challenge it is, I made just a traffic light for you for the different geohazards. So red is a big challenge, medium, lower challenge, and it's basically likelihood multiplied by impact. And I should really say this is based on my experience. So you may disagree. Please also share your thoughts on that. It's based on my experience, what I know from literature, and what we're working on at the moment. So it may be it's nothing reviewed by the community in general. But good, let's start with the complex infill, because that one, and that's a high likelihood, and it has a high impact on your engineering. If you're dealing with a tunnel valley that just has one type of infill, then yeah, you're really lucky, and that's good for you. It's not very common that you experience a very simple tunnel valley infill, because you're gonna have a lot of variations in grain size. These are some pictures from provided by Jan Piotrowski from Aarhus University, where we see some subglacial channels, and you see a lot of heterogeneity. You can see, like here, you have outward sediments, you have some till at the base, very coarse grain. We have cobbles in there. You may have sandy layers in here next to some softer sediments. So this really, it's more to highlight. We can really, from onshore, we can learn a lot what is actually possible to identify in these tunnel valleys. Obviously, a lot of borehole information from these features. So again, highlighting gravels, cobbles, pebbles in these sections of the tunnel valleys. And like here in the picture D, actually from the Lesemann paper, you see a big boulder at the base of that tunnel valley. It's really, this is more proximal to the ice sheet compared to what we're dealing with in the North Sea often. But yeah, a big boulder identified, big cobble beds at the base of a channel. So we should experience something like that. And if we hit these layers, obviously gravel and pebble beds, has an impact on the drivability, on the trenching, and also on the suction buckets. That's the key aspect that it actually hits when you're dealing with this, especially with gravel and pebble beds. I'm gonna have a slide on boulders later on separately. So staying with vertical complexity. So it's as you saw in one of the first slides, is often the CPTs or the boreholes, they're not hitting into the deepest part of a tunnel valley. So sections like this one from Adrian Jansen that are several 100-meter long and cover a complete tunnel valley infill, that's like offshore northern Germany, in the southern, let's say in the southern North Sea, where you really he has soft, thick sequences of soft clay, glacial outward sediments, so more medium sand, some till atop, several tills also below. really, it's you can have anything in there, and it's really showing vertically. You can go really from soft clay into a very stiff glacial till in the tunnel valley infill, depending on the how the deglaciation works, what happens below the ice, and also what then if it's overridden again later on. So it's really amazing what you can find there. And especially if we have soft beds, and that's also something that you can very commonly have, that has a big implication on the stability of your foundation, the foundation design per se. And also these soft beds, they have an impact on the trenching. So really vertical complexity, high likelihood, and also high impact when you deal with that aspect. So that's something that's I think that's the key message, how complex they are, vertical, but also lateral. So figure here to the right is tunnel valleys in the central North Sea mapped out by Kirkham, and the different colors are different generations. So you see it looks like a bunch of spaghettis or so, a lot of tunnel valleys in this, and it's a very small scale here, so just some few kilometers. And then below he was mapping out different type of infill. He deals with some of them may be infilled by shallow gas. So really a big challenge. For instance, if you have a wind farm project that covers now this acreage, and they can be much bigger than this, then you need a lot of data to really make a solid subsurface model and to make a good engineering evaluation as well. Because when we have lateral complex soils, the settlement may be really be different compared. Okay, let's say this is an onshore analog, but the soils actually may settle with a different magnitude in the tunnel valley compared to next to it. So really, lateral complexity is also a high risk because and you commonly have it. That's also very common to hit. It has implications on the shear strength and grain size predictions, because you cannot just assume that it's the same type of grain size along the unit. The units that you map out, that you deal with, it has an impact on the suction buckets, and as shown here, it also may be linked to differential settlement. So that's really important when you decide where to put the foundations. Here now, again, offshore Netherlands. This is now the structure map. So the depth, you see the tunnel valley here, in blue, the deepest of the channels, and here is now let's say the terrain the platform it eroded into. We can make this geophysical spectral decomposition, frequency blending, and you get much more information out. You see some debris flows into the channel, and you see this around circular depressions. And these depressions are particularly interested because they're kettle holes. So here kettle holes, again, here that's the outline of where we have the tunnel valley, some gullies. But focusing on the kettle holes, kettle holes are basically the remnants. You have an iceberg that is getting swamped over on an outwash plain, for instance. And it's, as long as it's not melted away, of course, nothing can deposit in here. We have a lot of really nice kettle holes in Iceland, onshore again. But they're really hotspots. Kettle holes are a hotspot for lateral variability. And this is now not in the tunnel valley, but they're really next to the tunnel valley. So you don't want to put your offshore wind farm foundation, so the turbine location, into such a kettle hole. I would rather go a bit, if you have the if the project allows you, rather go outside of them. But in order to have this control into the subsurface, you really need this type of ultra high res 3D seismic data that allows you to image these landforms and make conclusions about the infill. Good. This is a project from it's from the UK sector, central North Sea, an ultra high res 2D seismic profile. You see again a lot of channels. You see a very shallow channel. This is fluvial channel. You see some deeper channels mapped out as tunnel valleys. So all of these blue ones here, that's tunnel valleys, subglacial channels. This is fluvial channel up here, the pink one. What I particularly like about this data set is, you may say, okay, we mapped out tunnel valleys at a certain depth. They're all belonging to the same generation, like the blue ones here. We have a CPT here. We have a CPT here, then here to the right as well. But you see there, it's completely different. Here on the right one, you have clay, maybe with some gravel, sandy infill, but mainly soft clay. And then you're just maybe some 8-9 kilometers away in a tunnel valley where you have mainly sand. And from a geophysical point of view, I'm sure that the tunnel valley infill, just 100 meters away from this sandy one, is again completely different compared to the one I have the cursor on now. So it shows us really how heterogeneous the infill in tunnel valleys on these small vertical and lateral scales can be, and how important it is really to ground truth the infill. So you can really, unfortunately, you cannot make conclusions just based on, yeah, I know what's in here. Go 100 meters away and tunnel valley, you may say, from the same time, but completely different infill. So really complex, and it highlights the use for spatial control of the infill, and where we may have some flank collapses like here, or more some sandy outwash like here, and then this one may have been covered, filled in by a lake. So it's really key to integrate all existing high resolution data, geotechnical data, geological data, to make the most robust ground model for your offshore wind farm, or also when you're just making a foundation principle for, let's say, for an oil and gas platform. Okay, lateral and vertical resolution variability, big risk, very common. What about boulders? And boulders is a bit, I told you before, we have some boulders onshore in tunnel valleys and glacial channels. Offshore, usually a boulder in geophysical data would be recognized as this circular kind of reflections, diffractions in a profile view. We have some migrated data sets, but you better use the unmigrated data set to map them out. So really nice boulders in here, but this is not from a tunnel valley. This example is just an amazing example from a Vattenfall project collected by GeoSurveys that shows us how boulders are supposed to look like. However, in tunnel valleys, I have not a lot of examples, or I lack really good examples on boulders in tunnel valleys. And if you have some good ones, please share them with me if you're allowed to. I'm very much interested, because from onshore, we know there could be. The problem we have, often with a lack of data in the deepest part of tunnel valleys. So they're not going, our boreholes or CPTs may not reach the deepest part where we could have the boulders. And maybe we're not at the right location sometimes to hit the boulders, which is maybe positive when you're thinking about your design, but it would be good to know really where they're located. And for instance, in Kirkham's model that I showed in the beginning, in type 1 formation model, we may have boulders in the debris lobe, like right next to the glacial margin. So it's important to know then where the glacial margin is, and could we have a lot of boulders then located here? And another question is also still like here in the lower right corner. Most likely tunnel valleys, when you think about boulders, are good areas. You won't hit a lot of boulders most likely in the tunnel valleys compared to the neighboring areas where you may have glacial till. So it could well be that the tunnel valley is eroded into the glacial till, but then still, couldn't the boulders have been fallen down to the very deepest part of the tunnel valley? So that's the question. Most likely, if they're located somewhere, they may be well here at the very deepest part. And again, the very deepest part may be glacial till, and then for sure there could be boulders in the tunnel valleys. But yeah, that's why I have at the moment green, yellow, so not too likely. Of course, if we have them, a very high impact, but from my experience, not very likely to have them. That's why I could not really decide what color I give them. And obviously, if you have boulders, you have big problems with drivability and also with trenching. Good. Next challenge, gas hydrates, permafrost, frozen grounds, like we have often offshore like in Alaska or in Siberia, terrestrial platforms, where you really freeze the uppermost meters of the ground. This is another example from the Netherlands, from that wind farm there. This is the structure map, and you don't see a lot of features. You just see here the tunnel valley to the right here with the cursor. However, if we do spectral decomposition, frequency blending, or also some seismic amplitudes, you see these polygonal faults, and therefore that's an indicator of that you have permafrost, and that the thawing and freezing of the permafrost may may kind of have an impact on your soils. So periglacial processes, like we have in, this one is from Alaska, I think. These nice polygons, we can observe them in ultra-high-res 3D seismic data, and they indicate that we may have decomposed some of the uppermost meters, and they may be weaker substrate, even if in the bedrock, than you may assume. However, usually that's we can identify that in the seismic data, and that's why the likelihood is maybe medium, so it can well happen in the vicinity of tunnel valleys, but the impact is not too big, so we can really, engineering-wise, we can deal with this. So, but it's important to have an eye on this as well, periglacial processes, because they may form weak layers. Implications are weak layers, and they can also be, there might be a likelihood of potential gas as permafrost. Yeah, you freeze water, but you may also freeze, you may even freeze up some gas or seal some gas that would seep out into the water otherwise. Good. Another geohazard or geoengineering constraints, it's faults and deformation in the infill. So we may have faults and deformation. It's, in my experience, it's not too high likelihood, so it's not very often that you observe that. The impact is kind of medium. In that infill offshore the Netherlands, you see here some very nice faults. They're not big. It's less than a meter. It's some decimeters, the offset here of the faults. But they may indicate some implications for differential settling. And we see also some of this in the planar view. So if you do the spectral decomposition, you see here again our famous tunnel valley, a very beautiful tunnel valley. You see a big river coming from the side here, feeding into the tunnel valley. But you see also some of the soft clays here that are having these nice ridges or ripples, however you want to describe them. And they're actually in the seismic data correlating soft clay, but correlating with this small offset faults. And they may be of a, it's not a big challenge if you identify to tackle it. But deformed sediments, obviously, if you have faults and deformation, you may have some deformation problems. And it could also be that these faults are acting as fluid migration pathways. So be cautious, especially if you work in the Baltic, for instance, where you may have a lot of shallow gas. Good, but it can be observed in tunnel valleys. Good, we were talking about gas, about the composition of material. Peat, organic, high organic material, is very often observed in the very near shore areas of the North Sea. Obviously, peat, here the peat layer at around 4 to 5 meters has a very high organic content, and they're very important for the thermal conductivity. For tunnel valleys, it's not so likely because they're too deep usually to have peat. The impact, obviously, I say now medium because we can deal with it if we identify it. And peats often can be identified as a high amplitude seismic reflections in draping channels or filling in some small channels. There's a lot of studies on the Paleo Valley of the Elbe, where you may have peat layers that affect, but it's more for the cable route when you're in that stage. So peat layers, high organic, may occur in the very uppermost part of tunnel valleys, and they have an impact on thermal conductivity when it comes to overheating of the cables. Be cautious when you plan the trenching, and also if you drain the peat, also the differential settlement may be quite a challenge that you can hit when you're dealing with peat. Second last challenge, the shallow gas. Shallow gas, again, is not so likely to have in tunnel valleys. But if you have it, for geohazard experts, always shallow gas is usually the first they look for. And this is an example from the central North Sea, where we have some shallow gas accumulations in parts of a tunnel valley infill related to gas migration along faults. And what was very nice in this figure of that paper from Kirkham is the gas seepage that could even be discovered in the bathymetric data set in the water column. So you even see that where it's actively coming out, and it can be correlated to tunnel valleys. Yeah, so that's shallow gas. Have a look, an eye on that, but it's not as common as lateral and vertical variability. But obviously, if you have indications of shallow gas, engineering constraints would be the blowout, which yeah, that's a worst case scenario. Really avoid that one. Then the clearance for the borehole drilling has been to be done in a very early phase of the project. And shallow gas will also reduce the shear strength of your sediments, even if it's not a problem for of a blowout. Maybe it may still have an impact on the engineering by reducing the shear strength. Good. Last point, slope instability, and that's a medium likelihood and also has a medium impact. It's very, yeah, you can have it quite in some of the valleys, often disturbed beds that fail into the deep part of tunnel valleys. Also imaged here along the flanks, some coarse-grained pebbles and gravels that fill the tunnel valley and that can be identified as high amplitude reflections. And we see also some slope and instability, so lateral spreading, failing of the flank of the tunnel valley into the deeper part. So really be cautious when you have some indications of slope instability. Also fantastic paper from Lasse Printz, Geos. He mapped out a lot of tunnel valleys and he used time slices to identify where the slope failure is coming from. So that you see up here. So the areas where it's coming from, and then where do we have the deposits? Where do we have these coarse-grained debris lobes of the slopes failing into the tunnel valley? So it's really, again, beneficial to have ultra-high-res 3D seismic data to deal with that. When slope stability, it's a big concern because it has an impact on protection, on stability, and also you may have a lot of grain size variations in the deposits. Good. So to finish up my talk, way forward, what I think is important for the future, or where do we have challenges? So often we're located in complex glaciological areas, and often we have some geophysical data, coarsely spaced, densely spaced 2D seismic lines, some boreholes, some CPTs that are not correlating with the geophysics. And then we say we want to have a turbine here, 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 and here. But we do not, sometimes in the beginning, we do not know what the surface is like. And really what I want to highlight is the importance of having good lateral control. If you have a conventional or densely spaced 2D seismic data set, that's how the subsurface is looking like if you map it out. And we can just improve it and push it towards the meter size. And all of a sudden you notice, okay, actually, if I put my the wind farm foundation at this location, I may be partly in glacial lake, partly in a delta. Here I may be in a fluvial channel or in a moraine up here. So it's really what I want to highlight. Glacial terrains are extremely complex, and so are the tunnel valleys. So we really have to be cautious how we evaluate the subsurface. And using an integrated approach, we can suggest wind farm turbines, but we should really be open when we, for instance, see boulders like the white dots here, to say, okay, if the footprint is now 25 meters and I still have, it's accepted to shift it by some tens of meters, then that should be, in my opinion, that should be done in order to make it more safe and robust. So there is really a big benefit on using ultra-high-res 3D seismic for that purpose. Onshore analogs should be used more often because they are really beneficial, especially if we don't have data collected from the deepest part. So use analogs. Academia does that quite intensively, but that should be strengthened, in my opinion, because really, yeah, where we lack data, they can help us a lot to characterize and draw parallels and speculate the risk. We still have an uncertainty, but it should be lower than if we don't include analogs we can tie into. And then inversion, data propagation, also that should be done more and more. You see here that's a seismic profile from this, from offshore, also the Netherlands, subsurface of around the uppermost, let's say 50, 60 meters. Here the red reflections I draw are the two last glaciations, the Weichselian and Salian. And if you have the geotechnical information, you can now propagate and characterize your soils. Again, here you see a tunnel valley, here another one, and you see how heterogeneous they can be if we feed acreage that has no geotechnical data and propagated in 3 dimensions. And we can play obviously with different parameters. So here I show the cone resistance. This is done with Elise, Emma Legal and Benjamin Durand did this, and together with in collaboration with us. Or we can also study how the friction ratio evolves in a tunnel valley. And again, you see a lot of variability in those. And in the end, it's really the product when we talk about engineering and geohazard is to develop a very robust ground model. Like I showed a lot of examples from offshore Netherlands, NGI and SAND. We did a ground model there where we really integrated all the information in high resolution, and that's really required to make a solid subsurface model, and it's really complex. I also think that the channels, they deserve even more attention than what they got in the past. So really my R&D focus is really to bring out more of these channels and make it safer to either to decide not to go into them, or if it's not possible to avoid them, to make installation safer in channels as well. Good. So to conclude my talk, I checked I still have some few minutes. State of research, geophysicals, the geophysicists. So we have really, tunnel valleys are identified on quite a regional basis, and the data is often published. So it's really good. For where we have data published, we know where they're located. However, the drawback is the characterization of the infill. That should be improved in geophysical data. Geology, we need boreholes that cross complete tunnel valley infill, and that's not very common. At least the ones that are published are not common. Maybe companies have a good amount of examples. Edge control of the infill is still quite weak, and we have some fantastic onshore analogs in outcrops. And then when it comes to geotechnics, I know from NGI there is hundreds of CPTs in energy companies, especially due to offshore wind, that are collected. But the drawback there I see, it's often not published. So we cannot really say too much from other areas if we don't know, or if it's not really published. So the outlook I see in there for the research on tunnel valleys is really, first of all, a point in itself, how should we share such information and data? That would be a talk in itself. So I think that should be addressed. Geophysics, I know new and reprocessed 3D seismic data, that will solve a lot of it. And then also the quantitative interpretation inversion. Geology, better dating and tying. So chronostratigraphic models have to be improved. And also a better link to onshore. And then in geotechnics, with a smiley, I write a publication. So that would be nice to have more data published so that we can actually compare. And we need a lot of information CPTs per channel and also per WTG location in case we're gonna set a foundation there. So 3 points, please take them with you. Tunnel valleys are common landforms on formerly glaciated shelves. We have a multitude of geohazards and geoengineering constraints. And the main risk is lateral and vertical variability. And there is a paper by us. I can forward that if you send me an email, if you're interested. So I'm really interested in your feedback. I do not just say that to finish up my talk. So please share your thoughts or your question with me, benjamin.bellwald@ngi.no. And integration is key. We can all learn from each other about tunnel valleys, about geohazards, about geoengineering, and also when it comes to R&D proposals. So please let me know and share your thoughts. And also when it comes to marine geohazards and geoengineering constraints in general, please be open to share your thoughts with me. And with that, I would like to thank you for listening and to thank ECOSIGG to invite me for this talk.